Okay, and then if you ever need to find out how to import or export data, I recommend the quickest way is to just Google MATLAB file format and click on this first link that comes up, supported file formats, and that has the help page that looks like this that will show you all of the shorthand. And it's a little bit tricky for text files. You have to play around with it a little bit, but for Excel files, it's usually pretty straightforward, and then same with the .mat file. Here's just a quick debugging tip. These are two common errors you see when you're running code. They both mean that you're accessing parts of an array that don't exist. So I've created an array 1 through 10 up here in X. It has 10 elements, but remember that the subscripts or the indexing starts at 1 for MATLAB. So if you ever try to index with a 0, you'll get an error. And if you ever try to index with a number that's outside of the array, you'll also get a 0. The only time that this is okay is if you're creating this element. So if you had x11 equals 1, it would put an element in the 11th location. But if you're just trying to access it, it wouldn't allow it. You guys have any questions about that? Yeah?
So if you had like 1 through 10 defined, and then you defined like the 12th number, would it like create an 11th as well?
It does create an 11th. I think it makes it a 0. Yeah.
Is there a reason other than tradition MATLAB doesn't use zero-based indexing like every other language?
I don't know the answer to that actually, but it's really annoying because all the algorithms that we use were written for these other languages and they all start at 0 and you have to shift everything for MATLAB. I don't really know the reasoning behind it. Any other questions? I'll look into that for you. That's interesting. Okay. So we're going to start topic 8. And this is the pinnacle. I think I've already said that before. I don't even know what that word means, but like a big part. But this is a huge shift in the course, topic 8, which is why the midterm happens right in between these topics. So topic 8 is our first application. So topics 8, 9, 10, 11, and 12 are all going to be applications of what we've learned in the previous topics. So in all of these topics, we're going to use functions. We're going to import data. We're going to use loops. We're going to use arrays. We're going to use all of these things that we've learned. And a lot of it is based around data analysis, statistics, numerical methods, and different techniques that are used in engineering analysis. So the one that we're starting with today is a general topic called data analysis. Well, you can see my hand. Just can't see the words. And statistics. So other topics we're going to do are, I kind of forgot actually, interpolation, integration, differentiation, optimization, and linear algebra. 2 of them are new this year, linear algebra and optimization. So those will probably be really smooth sailing. This topic is trying to be able to understand a way that you can study a large collection of data. And that's just like a general definition for statistic. It's the study of the collection, analysis, interpretation, and presentation of data. So for example, with Lab 7, we're looking at this huge spreadsheet of all of this information about planets. And you can't possibly tell anyone anything about that data unless you do some sort of statistical analysis on it. You couldn't just give them the spreadsheet and then have any idea what this data means. And so the way you want to think about statistics is a way of taking a really, really complicated set of data and telling a story with it using metrics that you can define. So it's not hard to collect data. In fact, collecting data is very easy and finding data is also very easy. What's hard is to make any sense out of it, and that's what statistics does for us. So For all of these different statistical measures that we're going to be doing in this topic, we're assuming that we have a set of data. And so we use n as a general number of pieces of data. So it could be 100 pieces of data, 1,000 pieces of data. And the notation that we use is that it would be stored in a single array. So if I used the variable x, I would index it with I, and the I index would just follow the index notation that MATLAB uses, and each element would hold a different one of those pieces of data. And the example that I'm going to use for all of these is an array of test scores. So the first piece of data is a score of 65. The next piece of data is a score of 82. And so when you think about these different algorithms and statistical measures, think about this example of an array X that's holding scores. You could also use the word scores to label this array as well. Now the thing that's different about this class is that we are not only learning these concepts, like we're not only learning about statistics, but we're learning about how you write the algorithm for statistics. So all of these algorithms that we write in the rest of the topics are already written in MATLAB. There's an intrinsic function for them. But we're not using that intrinsic function because this is a programming class. And a lot of people, all of you, will probably hear at some point someone complain, why are we rewriting intrinsic functions? So I'm telling you that the reason is because you do not want me to give you an assignment where you have to write a function that has not already been written, because that would be very difficult. You know, you need to write an algorithm that is simple enough that you can understand the algorithm. So that's why we start with things like sums and means and those types of algorithms, because they really help us develop that skill. So I'm going to create this table of all the statistical measures. None of these are in your textbook. In fact, there's pretty much the rest of the class. There's not as much in the textbook. It's also not easy to find online. So I post these so you can always refer back if you write something down incorrectly. But you will need all of these equations on your toolbox card for the final exam. Not for the exam tonight, but for the final exam. So I'm going to create this table where I'm going to explain the measurement that we're going to be looking at. I'm going to define conceptually what it is. I'm going to define the equation that describes it. I'm going to explain what it measures, like conceptually what it measures. And then I'm going to write down the intrinsic function that does that same thing. So while we're writing these algorithms in our lab, we're going to want to use the intrinsic function to check to see if we're doing it correctly, basically. So we're going to start super easy with a mean. Everyone knows that. What's important with understanding these simpler ones is it can give you a better idea of how to read this notation, because depending on your background, this notation could be less familiar. So a mean takes an array of data. So x of I is our array of data. Think of it as all of these scores. And it sums the array over all indices, I equals 1 to n. And it divides by the total number of points in that array, 1 over n. So I think everyone knows what a mean is, but make sure you know how this notation works so you can understand what the more complicated ones mean. Any questions so far? Anything you can't read? Now, what is a mean measuring? In general, a mean gives you an idea of the central tendency. It's also a form of an average. Technically, the word average in statistics is not the same as the mean. The mean is actually this exact thing. The word average is a more general word for telling you some central tendency, basically. And so it gives you an idea. And so like if you guys all took your exam, like tonight, and then I told you what the mean of your exam scores was, that would only give you some idea of how the class did, right? It wouldn't really tell you the distribution of the scores. It would just tell you a little bit about how it went. I wouldn't want to give you a list of all the scores. That also wouldn't be very useful. So it's this idea of like, how could I communicate to you how the exam went, how the scores went, by telling a story with some of these statistics. We've used this function in MATLAB, and the intrinsic function is just mean, so it's pretty easy to remember. Some other ones are median. The algorithm for this is, there's no mathematical way to represent what it is, but it's the middle value. And sometimes if the middle value is two values, you take the average, and sometimes you take one or the other. So the algorithm is really interesting to write because you have to write an algorithm that locates the middle value. And there's actually several different ways you can do that. It also just tells you some central tendency or average quantity about this set of data. And then the intrinsic function is median. The mode is the next one, and it's the most frequent value. It's also a really interesting algorithm to write. And there's no way to define it just mathematically like you can with the others. It also just gives you another idea, like the mode is, I don't want to say this with these scores, it's feels like I'm torturing you, but I'll do a high one. The mode was 95. That means that was the most frequent score that people received. But the mode, there could be only 5 people that had that, and everyone else had a different score. And then the intrinsic function is mode. So we will look at these algorithms, but for now, we're going to look at standard deviation. It's the first one that you write in the lab. So the standard deviation, the equation for that is you take every data point, xi. I'm really sorry about my voice. I'm not that sick, but my voice sounds like this. I feel fine. You take every data point, you subtract off the mean. So it gives you an idea of how much every data point varies from the mean. You square it, mostly to get rid of whether it is above or below the mean. You just want to know how close it is to the mean. And then you sum those values over the entire set of data from 1 to n. And then you divide by 1 over n minus 1. Some definitions of standard deviation divide 1 over n. You're just normalizing it by the number. But I'm using this because this is how MATLAB does it. It uses this definition so we can compare. And then because you squared the values in order to get back to the same kind of units or quantity that you started with, you're going to go back and do a square root. So that's the standard deviation. It's also called the RMS value, which stands for root mean square. So you've probably seen both. And you've probably seen this in Excel or other software packages that you've calculated it. So that's the equation. So you can see that in order to define the standard deviation, you already have to know the mean. So it is measuring the variation from the mean. That's what it is. And another way to think about it is it tells you how spread out your data is. So for example, on exam scores, having a high standard deviation is not good. You don't want to have your scores spread out over a large number. That means that the exam was bad. Don't tell any faculty I said that, though. And then in MATLAB, conveniently, the intrinsic function is STD of x. So that's what you can use to check to see if that algorithm is working, because you will be writing that algorithm in your lab. Now there's another version of the standard deviation called the variance that you've probably heard of. It's basically the same as the standard deviation, but you just take out the square root. And it's used for other calculations, so you will need it. It measures the same thing, it just has a different, I guess you could just say a different unit. And in MATLAB, it's the intrinsic function is var. Okay, the last statistical measure we're going to do is the final one that you're going to program, but you need pretty much all of this in order to program it. So we need another set of data in order to understand the last one. So y is another set of data. And we'll call it yi. And it's the same thing where I is just the index in MATLAB from 1 to n. And I'm going to give you an example of a piece of y data that we could use to maybe compare with x. So I'm going to use number of days you missed of class. So 8 days is corresponding to the student who got a 65 score. So that student missed 8 days of class and got a 65 on the exam. 2 is the next one. So the person who got 82. Move it down. Oh, am I pointing to something you can't see? Sorry. 2 corresponds with a score of 82. And then I'll just finish. So 3, 10, 1, 0, 2, 4. This is not real data. I made this up to make a point. But let's say that we wanted to know, perhaps, does days that you missed of class correlate with the score that you got? How would you do something like that? So to do that, you calculate something called covariance. The covariance is very similar to the variance, except for that you are looking at how x varies with the mean, how y varies with the mean. You're multiplying them together, and you're summing them. Dividing by 1 over n minus 1, and we use sigma xy to define covariance. And it basically will tell you the strength of the correlation between two data sets. And then the intrinsic function is COV, and then you need 2 inputs to that function, the 2 pieces of data that you would like to compare. Now the covariance is nice, but it's not normalized by anything. So if you want to compare how correlated 2 different things are, the covariance depends on the magnitude of those 2 things. So we're not going to use covariance by itself. We're going to use something called the correlation coefficient, which basically normalizes the covariance. So we use Rxy as our correlation coefficient. We take our covariance and we just normalize it by the magnitudes of the variances of each x and y independently. What this does is it makes it so that the correlation is either a max of 1 or a min of -1. And I'll explain a little bit more what those values actually mean. And so it's normalized, so you don't have to understand the magnitude of the data to understand how strongly correlated they are. So if you've ever done a best fit line in Excel, that R value is what this is right here. That shows you how much the trend line fits. So it's the same thing but normalized. It's the same thing as the covariance but normalized. And in MATLAB, it's CORRCOEF. And then you put in the two pieces of data that you want to correlate. I'll leave the top of the table up there. Okay, a couple notes. So we're all going to be using the CORRCOEF intrinsic function to check to make sure that our function is working. This is actually what you're trying to write is a correlation coefficient function. So you're going to write this, but as you see, you're going to need to define a covariance. You're going to need to define variances and means to define this function. So when you call the covariance function, it's going to return an array. And it's always a little bit confusing when people are trying to interpret what it means. And this is true for the covariance and the correlation coefficient function. And what it's doing is, by default, it gives you the variances and the covariances. So for comparison to your function, you just want to compare your calculation with the off diagonal of that function. So whether you're comparing to the covariance or the correlation coefficient, just keep in mind that it will give you an array, and you don't need the whole array, you only need the off diagonal terms. So you can either use the variance function or the covariance function to get the variances, if that makes sense. It shows you both. Okay. So this is just, these are your rows and these are your columns. So you would just, you would save this to n, and then you would call 1, 2 or 2, 1, and that would get you just the off diagonal term. You can do either, they'll always be the same. Okay, so let's just talk a little bit about these correlation coefficients and what they mean. So correlation coefficients, the RXY value, will have a range of -1 to 1. So for R equals 1, that means that you have perfect correlation. So if I wanted to give you an example, I could say, I definitely should not just make one up because it's bad. But maybe something that's perfectly correlated would be something that has a definite relationship. So there's the time on your alarm when you wake up and the actual time in the universe or something. They're exactly correlated. They definitely relate to each other. So this is called perfect correlation. And it's in the positive direction. So let's look at something that's a little bit less correlated, but still positively correlated. So I could give you data like this. So just imagine I was printing two things that I was comparing, like test scores and attendance, participation, homework, anything. They're probably correlated very strongly. So this would be called high positive correlation. And then the lower you go, or the closer you go to 0, the more you're going to see the data spread out. but you still could maybe find a little bit of correlation. So this would be low positive. Then you can still have perfect correlation, but the correlation be in the negative direction. So if r equals -1, it's still perfectly correlated. Like for example, test score versus days missed. That's negatively correlated, but still correlated. So this would be perfect negative correlation. Yeah, sorry. And then I think you guys could imagine what the other two are like. And then the last one is something that is completely uncorrelated, which would be an R value really close to 0. And that would be just random, like it doesn't have any correlation at all. And this is more what most data looks like. A lot of times when you look at data, it doesn't look correlated at all, but when you actually calculate the R value, you can see a little bit of correlation. Now, I want to make a point, and I hope you guys know this. This isn't a statistics class, but we are going to be measuring correlation. And so as a scientist and engineer, you need to know that correlation and causation are not the same thing. And I'm going to ask you a clicker question next week, or I'm going to ask you that. And it's really important that you know that. Just because two things are correlated doesn't mean that one causes the other, or that one caused the other one, or vice versa. They could be both caused by something else. They could be totally random. So when you read a scientific study in the newspaper and it's like, oh, eggs are correlated with diabetes or something, like that doesn't mean it caused diabetes, you know what I mean? But we as scientists use correlation to give us an idea of causation by controlling the experiment as much as possible. And your lab is on climate data, so I have an opinion on it, but you can make your own opinion on what is causing what. So in the pre-lab, you're going to be working with the intrinsic functions, and in the lab, you're going to write your own correlation coefficient. But there's only one algorithm you have to write. Wow, I'm doing real bad with that. So the only algorithm required for the lab is to write a sum function. You need to prepare your pseudocode in advance for this lab. There's a lot of plotting, but the algorithm is fairly simple. It is a sum algorithm, and I'm even going to show it to you right now. Can you believe that? And it's a really nice algorithm because it's simple to understand, and you can't complain that I'm making you write a sum function, because once you write one, you can always use your own and never use the intrinsic function. Or, like most of you will do, you will rewrite this algorithm 3,000 times. But you can write this in a function and call your sum function, because we do sums constantly. So how does a sum function work? So who knows how to add up these numbers? Raise your hand. Just kidding. That's so dumb. Everyone knows how to add up the numbers, right? I mean, actually, I probably couldn't do that in my head, but like, you all get the idea. You take the first number, you add the second number, and then you have a sum, and then you add on the third number, and then you have a sum. So we basically want to tell MATLAB to do that very thing. So just like we did with the max function, or with a counter, we're going to create this variable, mySum, and it's going to hold the value of the sum. And then we're going to loop through all the elements of the array. And then we're just going to take that MySum value and we're going to add on to it the next element in the X array and replace the MySum with that sum. So MySum starts at 0. When I equals 1, it's going to add 65 to 0, and now MySum will equal 65. When I equals 2, it's going to take 82 and add it on to 65, and I already am going to stop adding. And it's going to keep adding on each element, and eventually MySum, when it finishes the full loop, will have the total value. So, say that? If I had a 2D array, what I would, let's say M is like, has 2 dimensions. I would create another array and I would just convert it into a 1D array and use the same algorithm. That's what I would do. But you could write a nested for loop that just looped through the i's and j's as well. Any other questions? Yeah, that makes it a 1D array. Yeah, so for those of you who had a quiz where you had to take the max, you could have done this. It was quicker, but most people have never done that before. There's a lot of other ways to do it. So let's talk about this piece that we're summing. So if we go back to all of these formulas, they all are just sums, okay? That's all they are, just a bunch of sums. So the only thing that changes is this value that you're summing. So if you need to sum something like this, for example, like for the standard deviation, you would just replace this with the entire quantity in the standard deviation. So it's the same algorithm. You can either write like 6 or 7 or 5 or however many sums you want like this with loops, or you can put this algorithm in a function and call it every time you need to do a sum, which is what I would recommend that you do. Okay, the last thing is great review for the exam. I'm actually serious. And also you'll need to do this in the lab. So you're going to find the correlation between all these different sets of climate data for Bozeman. And then you're going to need to put the R value that you found into the title of the plot. So in order to do that, what you're going to do is create a variable that holds the title that you would like to use. So my title is just going to say what the R value is. And so I want to actually put directly my variable into that title. So I'm going to create a string and use the num2str function that converts R into a string. And then I'm going to concatenate it with the R equals string, put the whole thing in an array. And then when I do my plot, I can just put this string that I already prepared directly into the title, and it will automatically have that variable into it. And this is a general comment about display statements as well. So if you want to do a display statement and include a variable in the display statement using the disp function, this is how you do it. With fprintf, remember that's a completely different syntax. We use the percentage sign, so that's different. But for disp, titles, or anything on a plot, this is the syntax that you use. Any questions about any of that to prep you for Lab 8? Okay, now just forget about all that, and I'll see you at the exam.